Welcome to Aerodynamics, Lesson 2.1. Here's an overview of what we're going to discuss today. These are your terminal objectives for the course. Keep in mind that these terminal objectives are for Aerodynamics 1 and 2. The enabling objectives for the basic theory of aerodynamics, you will see these at the beginning of each lesson guide, but they are located in your textbook. These are where the test questions will be derived from. Scalar versus vector quantities. A quantity that represents magnitude only is a scalar quantity, whereas a vector quantity represents both magnitude and direction. Examples of vectors are displacement, velocity, acceleration, and force. Vectors are important for aviation because they may be added together. So what we have here is vector 1 and vector 2, adding them together by placing the tail of the second vector on the head of the first, and then connecting them, I get a resultant vector, or vector 3. Force, the push or pull exerted on an object. It is a vector quantity, meaning it has both magnitude and direction. The example given is the thrust produced by a turbojet or turboprop engine. Mass, volume, and density are all scalar quantities, meaning magnitude only. Mass is the quantity of molecular material that comprises an object. Volume is the amount of space occupied by an object. And density, or rho, is mass per unit volume. So on the right side of the screen, we have mass over volume, or mass per unit volume, is equal to density. For aerodynamics, we'll be discussing air density. Work is done when a force acts upon a body and moves it. It is a scalar quantity equal to the force times the distance of displacement, or S. So what we can see here is if we have zero power is another scalar quantity. It is the rate of doing work, or work per unit time. So we can see by the equation power equals work over time. If I have zero displacement, I do zero work, which means 0 divided by time would equal 0. So 0 displacement, 0 work, 0 power. Power can also be measured by force times velocity. Horsepower is the amount of power being produced by an engine. It is calculated by dividing the results of either power formula above by 550, which is just a conversion factor. A very large force applied to a body that does not move, once again, does zero work, and if it does zero work, it therefore produces zero power. Force is mass times acceleration. We can also rearrange this equation to solve for acceleration. So acceleration is equal to the force over the mass. Weight, force, and moment are all vector quantities. Weight is equal to mass times gravity, is the force by which a mass is attracted towards the center of Earth by gravity. Moment is what is created when a force is applied at some perpendicular distance from an axis or fulcrum, which produces a rotation about that point. The distance from the axis or fulcrum to the point of force is called the moment arm. Once again, moment is equal to the force times the distance, or the moment arm. So what you can see is as you increase the distance, you can decrease the force to have the same moment applied. meaning it's an inverse relationship. Energy comes in two forms, kinetic energy and potential energy. It is a scalar measure of a body's capacity to do work. Total energy is simply the sum of kinetic energy plus potential energy. Potential energy is the ability of a body to do work because of its position or state of being. So looking at the equation, you have it equal to weight times height or mass times gravity times height. Kinetic energy is the ability of a body to do work because of its motion. It is a function of mass and velocity. So kinetic energy equal to 1/2 mass v squared. Next, we have this concept of conservation of energy. What it means is energy cannot be created nor destroyed, but can only transform from one form to another. Kinetic to potential or potential to kinetic. The example given is a T6 in level unaccelerated flight at a constant altitude and airspeed. Both kinetic energy and potential energy are constant. However, if we were to push the nose over and descend, we would transform the altitude loss, or potential energy, into increased airspeed, or kinetic energy. Next, we will discuss Newton's 3 laws of motion. Newton's first law of motion is the law of equilibrium, which states a body at rest tends to remain at rest, and a body in motion tends to remain in motion in a straight line at a constant velocity unless acted upon by some unbalanced force. This tendency for a body to remain at rest or in motion is called inertia. The graphic off to the right of the screen has all 4 forces of flight: lift, weight, thrust, and drag. Equilibrium exists when the sum of all forces and the sum of all moments around the center of gravity equals 0, meaning my lift is equal to my weight and my thrust is equal to my drag. For an example of equilibrium flight, you have a T6 in which all 4 of those forces sum to 0. Trimmed flight exists when the sum of all moments around the center of gravity is equal to 0. In a constant angle of bank turn, the aircraft is in trimmed flight, but not in equilibrium. The second law of motion is the law of acceleration, which states an unbalanced force acting upon a body produces an acceleration in the direction of the force that is directly proportional to the force and inversely proportional to the mass of the body. When the thrust of an aircraft is greater than the drag, the excess thrust will cause the aircraft to accelerate until the increasing drag equals the thrust, and once again I find equilibrium. Newton's third law of motion is the law of interaction, which states for every action there is an equal and opposite reaction. This law is demonstrated when the rearward force of an aircraft propeller's prop wash causes an aircraft to thrust forward at an equal amount of force. Atmospheric properties. Starting off with static pressure. Ambient static pressure is a measurement of the weight of a column of air over a specific area. As altitude increases, there are less air particles in a given column of air. Thus, ambient static pressure is less, because the column of air above you weighs less. Air density is total mass of air particles for a given volume, or mass per unit volume. As altitude increases, the distance between particles is greater. Therefore, as altitude increases, air density decreases. Air is compressible. When under pressure, air compresses into a smaller volume. The distance between particles gets smaller, thus causing density to increase. Temperature is the measure of the average kinetic energy of the air particles. Air temperature decreases at what's called a standard lapse rate, and that's going to be 2 degrees Celsius or 3.57 degrees Fahrenheit per 1,000 feet. It's going to continue to follow the average lapse rate until about 36,000 feet, and then it will remain constant. Humidity is the amount of water vapor in the air. As humidity increases, air density decreases. So if you look to the graphic on the right-hand side of the screen, you'll see the water particles are pushing the air particles further apart, which is decreasing the air density. Viscosity is a measure of resistance to flow or shearing. Air viscosity increases with an increase in temperature. Local speed of sound. Sound waves travel through the air as a series of compressions and rarefactions. The local speed of sound is the speed at which the waves of sound travel through the air. The speed of sound is directly dependent upon the temperature of the air, meaning as I increase temperature, I increase the speed of sound, and vice versa. The standard atmosphere is a set of reference conditions giving average values of air properties as a function of altitude. For the remainder of this course, we will assume standard atmosphere, unless otherwise stated. The general gas law is a relationship of the four properties of air, which are pressure, density, temperature, and the universal gas constant. By the equation on the right-hand side of the screen, you can begin to make relationships between various properties. If you increase temperature but keep density constant, the pressure must rise. An example of this would be a pressure cooker. If pressure is kept constant, then there is an inverse relationship between density and temperature. Steady airflow exists if at every point in the airflow, the following four properties remain constant: pressure, density, temperature, and velocity. Streamlines are the path that air particles follow in steady airflow. A stream tube is simply a collection of streamlines. In a closed system, total mass and total energy must remain constant. Since the total mass in a stream tube must remain constant, the mass flow into a stream tube must equal the mass flow out of the stream tube, which is the continuity equation. Static pressure, or P sub S, is the force that molecules of air exert on each other by their random movement. Potential energy per unit volume. The graphic on the right shows a fireman with the nozzle closed on a fire hose. We have zero movement of water In the tube, with no movement, I have very high static pressure, or high potential energy. Dynamic pressure, P sub D, or Q, is the measure of impact pressure of a large group of air molecules moving together. It is the pressure of a fluid resulting from its motion. Q is equal to 1/2 rho v squared. As we watch the fireman open the nozzle with high static pressure, we'll see the water molecules begin to move. As they increase in velocity, the overall pounds per square inch, or PSI gauge, will begin to drop. Total pressure, P sub T, is simply the sum of static and dynamic pressure. Subsonic airflow. Changes in density due to compressibility can be disregarded. So the formula looks like the one at the right side of the screen. Area 1 times velocity 1 is equal to area 2 times velocity 2. If the cross-sectional area on one side of the tube decreases, the velocity must increase so that the mass flow remains constant. Remember, the mass flow into a system must equal the mass flow out of a system. Daniel Bernoulli was a Swiss mathematician who described the variation of pressure exerted by a moving mass of fluid with the formula to the right. His equation shows that total pressure is constant for an open, continuous flow of fluid. Pressure total is equal to pressure static plus 1/2 rho v squared, or Q. Since total pressure is constant for all points in a stream tube, if dynamic pressure increases at a point, then static pressure must decrease at the same point. In the stream tube to the right, dynamic pressure over the airfoil in the tube increases because the fluid velocity increases. Therefore, static pressure must decrease at the airfoil surface. Altitude measurement. Altitude is the height above a given plane of reference. True altitude is the actual height above mean sea level, or MSL. Pressure altitude is the height measured above a standard datum plane. The standard datum plane is the actual elevation at which the barometric pressure is equal to 29.92 inches of mercury. On a standard day, the datum plane is at sea level. This means that on a standard day, pressure altitude will equal true altitude. Density altitude is pressure altitude corrected for temperature deviations from the standard atmosphere. Density altitude is not used as an actual height reference, but rather as an index for measuring aircraft performance. On a standard day, density altitude will equal pressure altitude and true altitude. However, at higher temperatures, air is less dense, and density altitude increases. On a hotter than standard day, density altitude is greater than true altitude. This is important because flying an aircraft when density altitude is high means the aircraft will perform as if it's operating at a higher altitude. Therefore, performance will decrease. High density altitude results in less engine power, since fewer air molecules are available to burn, and the propeller will create less thrust when it has fewer air molecules to push aft. Reduced power and thrust decreases acceleration and climb performance. High density altitude also requires higher true airspeeds for takeoff and landing, resulting in longer takeoff and landing distances. In order to measure our airspeed, we use the pedostatic system. It is simply a version of Bernoulli's equation, rearranging it to solve for Q, which we know is 1/2 rho v squared, or dynamic pressure. The pedo tube measures total pressure. The static port measures static pressure. And by taking the difference, we will get our dynamic pressure. This is transmitted to the pilot on the airspeed indicator. The airspeed indicator shows dynamic pressure displayed in airspeed. It is displayed in knots instead of pounds per square inch. A knot is a nautical mile per hour. In aviation, we do not use statute miles per hour. A nautical mile is roughly 6,000 feet. This airspeed indicator is preset at the factory for a standard day at sea level. Calibrated airspeed is indicated airspeed corrected for either indicator or instrument error, or for minor sensing and installation errors caused by the location of the pedostatic system on an airplane. Equivalent airspeed is calibrated airspeed corrected for errors caused by compressibility effects. One compressibility effect that causes an error is when air molecules bunch up and cannot flow freely through the pedo tube at high airspeeds. True airspeed is the actual velocity that an aircraft is moving through a volume of air. Equivalent airspeed corrected for density. For most subsonic airspeed conversions, the corrections to calibrated and equivalent airspeeds can be ignored. True airspeed is equal to the square root of rho naught over rho times our indicated airspeed. Once again, true airspeed is the actual velocity that an aircraft is moving through a volume of air. Since air density decreases with an increase in altitude, true airspeed will increase if indicated airspeed is held constant while climbing to a higher altitude. Ground speed is the speed at which an aircraft moves relative to the ground. It is true airspeed corrected for winds. True airspeed minus a headwind or true airspeed plus a tailwind will give you your ground speed. The example given is a T-6B flying at 240 knots true airspeed into a 20 knot headwind would have a ground speed of 220 knots. Another example is an F-18 Charlie flying at 300 knots true airspeed with a 50 knot tailwind. It would have a ground speed of 350 knots. ICE-TG is a helpful mnemonic for remembering the flow of airspeeds. An aircraft is any weight-carrying device for flight, supported by either buoyancy or by the dynamic reaction of air against its surfaces. In order to be considered an airplane, an aircraft must be heavier than air, fixed wing, engine driven, and supported by the dynamic reaction of airflow over its wings. The major components of an airplane are fuselage, wings, the empennage, landing gear, and an engine. A truss fuselage consists of a metal frame with a light skin stretched over it. The strength is in the frame. It is very strong and easily overhauled. However, it is very heavy. A monocoque fuselage consists of only a skin which provides all of the structural strength. So if it is full monocoque, it is only skin providing the strength. This is very strong and very light, but it is difficult, if not impossible, to fix. Semi-monocoque fuselage, which is what is used on the T-6B, consists of stringers, transverse frame members, and a skin over it. The strength is provided by all three components. It is strong, light, and easily overhauled. The wings of the T-6B have no external bracing, and therefore can be considered full cantilever. Ailerons are attached to the outboard portion of the trailing edge and are control surfaces that provide lateral control, or roll. Spoilers deploy only on one side at a time and produce motion by spoiling lift on that wing. The empennage consists of the aft part of the fuselage and has two components, the vertical stabilizer and the horizontal stabilizer. The vertical stabilizer prevents uncommanded yawing about the vertical axis. The rudder is a control surface attached to the vertical stabilizer and provides directional control, known as yaw. The horizontal stabilizer prevents uncommanded motion about the lateral axis. The elevator is the control surface attached to the horizontal stabilizer, provides longitudinal control, or pitch. Stabilators produce a change in lift by changing the angle of incidence of the airfoil. The entire horizontal stabilizer is moving. The landing gear of an airplane permits ground taxi operation and absorbs the shock encountered during takeoff and landing. The T-6B has tricycle landing gear arrangements. The purpose of the engine is to provide thrust. The T-6B has a Pratt & Whitney PT6 Alpha Tech 68 turboprop engine. An airfoil is a streamlined shape designed to produce lift as it moves through the air. Mean camber line, or MCL, the major design feature of an airfoil. It is a line drawn from the leading edge to the trailing edge halfway between the upper and lower surface of the airfoil. A chord line is an infinitely long straight line drawn through the leading and trailing edges of the airfoil. A chord is a segment of the chord line measured from the leading edge to the trailing edge. Root chord is a chord at the wing root, and tip chord is a chord measured at the wing tip. The average chord is simply the average of all chords from the wing root to the wing tip. Camber is the curvature of the mean camber line of an airfoil. Camber is measured by finding the maximum distance between the mean camber line and the chord line. Three types of airfoils are symmetric, positively cambered, and negatively cambered. And a symmetric airfoil has zero camber, meaning the mean camber line and the chord are the exact same. A positively cambered airfoil has the mean camber line above the chord. This will produce lift at a zero angle of attack. A negatively cambered airfoil has the mean camber line below the chord, meaning at a zero angle of attack, it will produce negative lifts. Wingspan is the distance from wingtip to wingtip. The T6B has a wingspan of 33 feet 5 inches. Wing area, or S, is the apparent surface area of a wing. It is approximated by multiplying the wingspan by the average chord. Wing loading is the ratio of an aircraft's weight to the surface area of the wings, or weight over surface area. Wing taper is the reduction in the chord for a given airfoil from the root to the tip, and is measured by dividing the tip chord by the root chord. Reduced weight and increased structural stiffness compared to a rectangular wing. Sweep angle is the angle between the quarter-chord line and a line parallel to the lateral axis of the aircraft. The T6B wing is both tapered and swept. Aspect ratio is the ratio of the wingspan to the average chord. An aircraft with a high aspect ratio, such as a glider, with an aspect ratio of 25:1, would have a long, slender wing. A low aspect ratio, such as 3:1, indicates a short, stubby wing, such as an F-35 or F-18 aircraft. A low aspect ratio is more associated with high-performance aircraft. There are two types of flow over an airfoil: spanwise flow and chordwise flow. Spanwise flow is airflow that travels along the span of the wing parallel to the leading edge. The airflow does not accelerate over the wing and therefore does not create lift. Chordwise flow is air that flows at right angles to the leading edge of an airfoil. Since it's the only flow that accelerates over a wing, it is the only airflow that produces lift. Pitch attitude is the angle of the longitudinal axis of an airplane and the horizon. Flight path is the movement of an aircraft through an air mass. Aircraft may have a nose-up pitch attitude with a descending flight path, and vice versa. Here we have an example of an aircraft with a very positive pitch attitude and a descending flight path. Relative wind is the apparent motion of the air with respect to the motion of the aircraft. The relative wind is in the direction opposite the flight path. Angle of attack, or AOA, is the angle between the chord line of an airfoil and the relative wind. Angle of incidence is the angle between the airplane's longitudinal axis and the chord line of its wing. Dihedral angle, angle of the upslope or downslope of the wings when viewed from head-on. Upslope is considered dihedral, and a downslope is considered negative dihedral, also called anhedral. An airplane has three mutually perpendicular lines or axes that all intersect at the center of gravity, or CG. The CG is the point at which all weight is considered to be concentrated. As fuel burns and bombs and missiles are expended or cargo shifts, the center of gravity moves. Center of gravity is also the point from which all movements in all three axes are measured. The aerodynamic center is the center of lift, point where all aerodynamic forces are acting. The aerodynamic center is typically aft of the aircraft's CG to provide improved stability around the lateral or pitch axis. Longitudinal axis is a straight line from the nose cone through the center of the horizontal stabilizer. about which the airplane rolls left or right using ailerons. The lateral axis is horizontally perpendicular to the longitudinal axis. The movement about or around this axis causes the nose of the airplane to move up or down, called pitch, using elevator inputs or changes in flap configuration. The vertical axis is vertically perpendicular to the roll axis. Movement about or around this axis causes the airplane's nose to move left or right, usually due to rudder inputs. In summary, we talked about some basics, atmospheric properties, properties of airflow, altitude and airspeed measurement, the major components of an airplane, airfoils and wing properties, as well as the center of gravity. That concludes lesson 2.1 in Aerodynamics 1.